Inverse functions. If f and g are inverse functions, then f of g of x equals x for all x in the domain of g. Remember, we were talking about domain the other day, and that if it doesn't work on the inside function, it doesn't work for the overall, for this composite. And g of f of x equals x for all x in the domain of f of x. This is an important thing we're going to use. There's a specific type of problem that's going to come up that we have to know this. So make sure, I know you do know it, but just make sure that you can bring it back at any time. As soon as you think inverses, we should be thinking f of its inverse equals x. The graphs of our reflections about the line y equals x. The coordinate of the points of f of x are xy. Then for the inverse, they are yx. So what does that mean? They are switched. The domain of f of x is the range. Since the x and y values are switched, it's a range of f inverse, and the range of f of x is the domain of f inverse. Our process, set y equal to f of x, switch x and y, solve for y. I could actually add one more thing. For the very last line, change y to f inverse of x. Alright, draw the graph of y equals 2 to the x, graph its inverse. We know that y equals 2 to the x is an exponential growth. So it's looking something like that. We can draw a dotted line for y equals x, and if we fold the graph about that line, that piece on the other side, it's going to be its inverse. And it looks something like that. We know this point for the y equals 2 to the x at x equals 0 is 1. So on the inverse, the point will be 1, 0. Find the equation of the inverse. So we start with y equals 2 to the x, switch x and y. We have 2 to the y. So it is log base 2 of x equals y. Then we'll say f inverse of x equals log base 2 of x. In general, the inverse of y equals a to the x. The only thing that would change about this is instead of saying a 2 in all these places, we would have a. So our inverse would be log base a of x. The domain of the function, we can see the domain is all real numbers. So negative infinity to infinity. And the range will be the numbers greater than 0, not including 0. So we have 0 to infinity. The domain of the inverse function, the log, will be the range of the exponential. So it is 0 to infinity. We can also see that over here. It will never touch the y-axis. The range will be from negative infinity to infinity. Let's go to the next page. And we have a log base a of x. What does that equal? That's going to be x. And log base a of x will equal x. Hurry up. Why is this true? Hurry up. Think about that a little bit. You know, you can look at this and say a to the log base a of x is going to be x, but why? Well, it has to do with what we just spoke about on the other page. What does f of g of x equal? That equals if f and g are inverses, that equals x. This is true because f of x equals a to the x and g of x equals log base a of x are inverse functions. And that's the justification for both of those. So f of g of x equals g of f of x, which equals x. There is a special base. What is it? It is e. So we could say log base e of x is written as the natural log ln of x. So then I have another question. What is e to the ln of x or the ln of e to the x? This is x and x. Why? Because of this very same reason, they are inverses of each other. Now here are your log rules. Let's use this to find log base 4 of 5. We can do this a couple ways. We could use change of base. I want to show it just deriving it for right now. We'll set it equal to x. This can be transformed to an exponential equation. This is the base of the log. It becomes the base of the exponential. So we have 4 to the x equals 5. If we take the ln of both sides, we'll have x ln of 4 equals ln of 5, so x equals the ln of 5 divided by the ln of 4. In general, if we apply this and think of this as a here and an x there, we can apply this change of base, which will be log base, I'm going to call it b, for any base as long as it's positive and not 0, of x over log base b of a. Let's use this to solve some problems. First thing we want to do is isolate the exponential. So we'll have e to the negative 2x equals 4/3. Take the ln of both sides. Since the ln of e and ln are inverses, we just get negative 2x equals the ln of 4/3. Let's put that in parentheses. So x equals negative 1/2 ln of 4/3. And then you could type it on the calculator to figure out what that is. This next one usually stumps a lot of people when they first look at it. One of the problems is the fact that we have 3 to the x and 3 to the negative x in the same equation. Well, what does this 3 to the negative x equal? That would be the same as 1 over 3 to the x. Now, when you were first learned in algebra, then in algebra 2 and pre-calc, what would you do when you have a variable in the denominator? You want to get rid of it. So what could I multiply by that would get rid of this variable in the denominator? How about 3 to the x? So I would get 3 to the x squared plus 2 equals 4 times 3 to the x. Now, while we are in calculus, just in case I want to go over this idea, most of you are probably great at it. This cannot be multiplied together because an exponent has to come before multiplication. What do you notice about this equation? This is a quadratic with our variable being 3 to the x. Now, if you like it, you can continue writing as 3 to the x quantity squared, or you could write it as 3 to the 2x. It really doesn't matter, as long as you're realizing that it is a quadratic equation. So we'd want to look, can we factor this? Is there anything that multiplies to 2 but adds to give us negative 4? No. So what does that mean? That's right, quadratic formula. Now, one thing I'm a stickler on is making sure you label what you are solving for. We are solving for 3 to the x, so we can say 3 to the x equals negative b, so that'll make it positive, plus or minus the square root of negative b squared, so 16, minus 4 times the coefficient of this. You can see it maybe a little clearer there. It's 1. 4 times a times c, all divided by 2 times a. So let's simplify that. 4 plus or minus. This will be 8, so we have the square root of 8 over 2. And I'll write it over here just to get that simplification done. 4 plus or minus 2 root 2 over 2. So we have 2 plus or minus root 2, which means 3 to the x equals 2 plus root 2, or 3 to the x equals 2 minus root 2. Now, one thing you have to be able to do here is you have to be able to recognize, because if you're testing on something like this and you didn't have a calculator, you need to be able to determine if this is possible or not. Well, 2 plus the square root of 2, square root of 2 is about 1.4. That's a positive number. There's no problem with that. So we can find the ln of both sides. So we'll have x ln of 3 equals ln of 2 plus root 2. So x equals the ln of 2 plus root 2 divided by the ln of 3. What if you wanted to say, you weren't thinking ln of 3, but we wanted to take log base 3 of both sides? We could say x equals log base 3 of 2 plus root 2. That's not a problem. You can do either one. 2 minus root 2, 2 minus about 1.4. That gives us 0.6. Can 3 to the x equal 0.6? Sure. What can 3 to the x not equal to? An exponential function here cannot equal to a number that's not positive. So 0 and below, because recall when we are looking at the, let me bring it back, we have an exponential function here. It has the horizontal asymptote of the x-axis. It will never hit y equals 0, nor will it go below. So if this number was, for example, the square root of 5, you would have to say there's no solution here. But since this one's okay, we can say this is log base 2 of 2 minus root 2. And that's it for there. Solve this thing for y. There are a bunch of different ways you can go about doing this. And there's no one right way that you have to do. I could start and say this is the ln of y plus 3 quantity squared equals 5 plus the ln of x. Now I'm trying to isolate y. I'm trying to get that by itself. So I need to get rid of this ln. So that's a base e. So if I raise the other side, I'll get y plus 3 squared equals e to the 5 plus ln of x. This can be simplified using your exponential rules. E to the 5 times e to the ln of x. E to the 5 is some constant. What's e to the ln of x? That's just x, because they are inverses again. I wrote x and it should be 5. So e to the 5 times x, and we have y plus 3 squared. We need to solve this, so we take the square root. When we do that square root, what do we always have to include? Plus or minus. So we have y plus 3. And then we can look to determine, is it possible to have a positive or negative? And we have plus or minus e to the 5 halves times the square root of x. Now the square root of x is always positive, so this part here is going to determine everything we need there. So we'll have negative 3 plus or minus e to the 5 halves times the root of x. Now we have to make sure, does it work in the original? If I have negative 3 plus e to the 5 halves square root of x, will that work? Well, the negative 3 will go out with there, and I'll be left with some positive number. Sure. What about negative 3 minus e to the 5 halves root x? When I plug it in, the 3's go away, but I'm left with negative e to the 5 halves root x. Well, that's a negative number, and you cannot take the ln of a negative number. We can go back and looking at what we did earlier in problem number 3. So what we have to do is throw out that negative, and our answer is just negative 3 plus e to the 5/2 root x. Now it's not acceptable to leave this plus or minus off at the beginning and say, oh, okay, it will end up working out. You have to go through the entire process.